Hello, today we're going to be doing lesson 1.4 from our textbook, which is all about distance. We'll start by doing the warm-up problems seen in front of you on this warm-up problem slide. Go ahead and pause the video and take a few minutes to complete the problems, and then we will go over them. Okay, so let's start going over these four problems here. First one, how many different ways can you name the line? So go back to the last lesson, 1.2/1.3, and we talked about the different naming conventions, or the different ways to label our points, lines, and planes. And so if you remember, there are two main ways we want to label, we can label this thing. Number one is we look at the points on the line, and we know that we can pick any two of these points on the line and use them to help us name the line. So we have points A, B, and C. Okay, well, we can, for instance, draw something like AB, and then with a little symbol on top, right? Or we can do something like CA, right? As long as we're picking any two of the points and putting the line on top, we can call that accurate. Some people might want to call it something like line AB, right? Also okay, but we want to lean toward using the symbols. And the last way is you notice that we have the orange M over here, right? That M is supposed to denote the whole line. So we can actually call this is the second main way we learned about. We can just call it line M because of the little italics looking M over here that's hanging out on the edge of the line. Okay, so in total there's 7 ways to name this line, I believe. Should be line AB, BC, BA, CB, CA, and CB. Okay, so basically it's just a combination of all 3 of those points, putting them together, that's 6, and then the 7th one should be the M. Then the second question, find the measure of the segment SV, so this little piece right here, right? Well, we know that the whole thing, ST, is 4.1, and we know this segment right here, VT, is 2.6, and so to find SV, all we need to do is subtract the two numbers. So 4.1 minus 2.6 is just going to be 1.5. So the measure for segment SV is just going to be 1.5 inches. Okay, down here we have a word problem. So hint, hint, what does that mean? That means we probably want to end up drawing a picture, but let's go ahead and read it real quick. So a straight railroad track is being built to connect two cities. The measured distance of the track between the two cities is 160.5 miles. A mail stop is 28.5 miles from the first city. How far is the mail stop from the second city? Okay, well, first thing is first, let's go ahead and draw what we know. And we know we are dealing with a straight railroad track. So what do you think that's going to be? That, of course, is going to be a line. In this case, a line segment. So a straight railroad track is being built to connect two cities. All right, we'll call this one over here City A, and this one over here City B. The measured distance of the track between the two cities is 160.5 miles. Okay, so the measured distance between both cities, A and B, in total is going to be 160.5 miles. All right. A mail stop is 28.5 miles from the first city. Okay, so 28.5 miles away from city A is going to be a mail stop. We'll call that point M. Okay, so we know from the first city is going to be 28.5. Okay, and so in the end it says how far is the mail stop from the second city? So how far is point M from the second city, point B? All right, well, just like last time, we have 160.5 for the whole thing. We have 28.5 for A and M. And so we're really just trying to figure out what the distance is between M and B here. So if we do 160.5 minus 28.5 minus 28.5, in the end, we're going to get 132 miles. Okay, that's all there is to that. Not too bad after you draw a picture. Lastly, we want to find the value of x, all right, so the variable here, if rs, the whole thing, is 24 centimeters. And when we look at the figure they give us, between r and t, we know it's going to be 6x minus 4, and between ts, we know it's going to be 10 centimeters. So you and I both know intuitively that rt, right, this piece right here, plus ts, the second piece, when you add them together, it's going to equal rs, the whole thing put together, right? So in this case, 24. So we know this plus this equals 24. And so let's write that out algebraically. So we have rt, which is 6x minus 4, 6x minus 4, plus the second piece, so ts is 10 centimeters, so plus 10, and then equals the whole thing, which is going to equal 24. So equals 24. Okay. Now from here, we just combine like terms. Negative 4 plus 10 is just going to be a positive 6. So this becomes 6x plus 6 equals 24. The next thing we should do to get x by itself is to subtract 6 from both sides. Okay, we'll bring down what we have, so 6x, those cancel out, 6 minus 6 is 0, equals 24 minus 6 is 18, and then to get x by itself, we will just divide both sides by 6. So in the end, these 6's cancel out, and we are left with x equals 18 divided by 6 is just 3. So in the end, x is going to equal 3. So x equals 3, and that's the answer. If you want to figure out what RT equaled, you're just going to plug it right in, right? So 6 times 3 is 18. 18 minus 4 would be 14. So you would know RT is 14. Then again, the question is just asking for x, so don't feel like you have to do that. Okay, so those are the warm-ups. So let's move on to the content for today. Tutoring every day after school except Friday, starting at 3:45. If you're starting to feel like you've fallen behind in room 100. Today we're doing lesson 1.4, which has everything to do with what we call distance. The learning target for today is to apply the distance formula to find the lengths of line segments. So the real-world application of this is anything that has to do with maps and directions. Some of the careers you might choose might be something like geomapping, engineering, land surveying, stuff in the military, of course, is going to be using concepts tied to distance and distance formula on a grid, specifically on a grid or a graph, right? Kind of like we were talking about the GPS stuff last class a little bit. So same kind of thing there. And then let's go to the vocab terms for the day. Okay, there's only 3. That is going to be distance, equidistant, and Pythagorean theorem. Now actually with equidistant, we do have it listed here, but this really goes with the next lesson more. So lesson 1.7 midpoint, which is next, deals with equidistant a little bit more. So we're going to not deal with that one so much today. We'll just talk about distance and the Pythagorean theorem. So go ahead and take a second to write these down in your notes. The notes you'll turn in later for your classwork grade. So first word is distance, second word is Pythagorean theorem. Go for it. I'll talk about vocab or definitions in a little bit. Okay, so hopefully you paused the video and wrote all this down. Let's continue. Distance. So the definition of distance is formally here just says the distance between 2 points is the length of the segment between the points. Okay, all that really means, and I'll draw a picture for that, all that really means is we have a line segment, right? Just like we were going over last class. We'll call that line segment MN, like that. Okay, and we found the length of the line segment just by doing addition or subtraction or some algebra to figure out how long it was. Okay, what's different today is the distance is actually going to be trying to find the distance or the length between M and N while on a graph. And so because we're dealing with the graphs or the grids, that means we're going to be dealing with coordinates. So x comma y stuff, right? So really what this should look like, instead of point N and point M, if you thought about this being on a graph, we should really call this something like x1 comma y1. And over here, maybe call this x2 comma y2, which just means that we have 2 points. Obviously, they're going to be x comma y. Point 1 has the 1s here, and the second point is just going to have the 2s there. That's all that means. Okay. So when we're dealing with distance, it's finding the length between 2 points on a graph, and the graph we're going to have 2 points that are denoted with coordinates like this. Could be anything from like 10 comma negative 5 to 1 comma 2 to 3 comma negative 6. You know, anything like that is what we're going to be dealing with when it comes to distance. Okay, that's the second sentence of this definition. The coordinates of the points can be used to find the length of the segment. So the coordinates of the points, the x's and y's, can actually be used to find the distance between them. Okay, and that's all today's lesson is about. And then the second term that we're really looking at today is the Pythagorean theorem. And take a second to think about what you know about the Pythagorean theorem. But you probably remember that the Pythagorean theorem is going to be a squared plus b squared equals c squared, right? And the only kind of triangle we can use the Pythagorean theorem with is going to be a right triangle. So let's just draw something like a right triangle. And we would call this a right triangle because it has a single right angle, or a single 90-degree angle, which is going to be right here in this case, right? So we could only use the Pythagorean theorem for a triangle like this. And so it's important to know where each of the letters belong on this right triangle. C is always going to be where the hypotenuse is, right? And if no one has taught you how to easily identify the hypotenuse, I'm going to do it right now. Sometimes it gets confusing because triangles, you know, flip and turn and all this stuff, and they look kind of weird sometimes, and it's hard to determine where that hypotenuse is. And so I'm here to tell you that you are always, 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 always going to be putting C at the hypotenuse, which is opposite from where the 90-degree angle is. So you just have to ask yourself which side is not touching the right angle. And so that, of course, is going to be this side over here, the side that is opposite from the right angle, right? So this one is always going to be C. You can see the bottom leg down here is touching the right angle, and this leg over here is touching the right angle. So neither one of those can be the hypotenuse, which is where C is. Okay. Now, it actually doesn't really matter where you place A and B. Typically, we put A on the shorter leg, so down here, and then we put B on the longer leg, which is over here. But you can switch A and B all the time, and it doesn't really matter so much. But C absolutely has to be where the hypotenuse is, always opposite from where the 90-degree angle is. Okay. Now, why am I telling you all this? Well, when you go back to the Pythagorean theorem definition, this definition is just writing out formally what we were just talking about. So it says the Pythagorean theorem is a theorem that the square of the hypotenuse, so the square of C, right? We have a little 2 up here, that's a square. So the square of the hypotenuse, C squared, of a right triangle is equal to the sum of the squares. So C squared is equal to the sum, meaning addition, right, adding, the sum of the squares of the sides. So this side is squared plus this side is squared equals our hypotenuse squared. And so this entire definition here is easily shown by just looking at our Pythagorean theorem and triangle here. That's all the definition is saying. It's just formally writing out in English what we see in front of us right here. Okay, so we're going to be dealing with both of these today, as you'll find out shortly. Okay, so let's start with the baby stuff here. This is what I like to call the stuff that probably not very difficult to do. So all we're going to do here is figure out the distance or length, right? They're synonyms. The distance between the following letters, the line segments. So for AC, the distance between AC is going to be 1, 2, 3. That's it. So the distance here would be 3. For CE, the distance would be 1, 2, 3, 4. There's 4 spaces between them, so that's all that's going to be. BD is going to be 1, 2, 3, 4, 5. So it's going to have a distance of 5. And then CF is going to be 1, 2, 3, 4, 5, 6. So there is a distance of 6 between C and F. Okay? And that is all there is to that. So go ahead and now take about a minute to find the distances of these 3 line segments. Go ahead and pause the video and turn it back on when you have it. Okay, so back here, we're just trying to find the distances between these 2 points. So JK is 1, 2, 3, so there's just a distance of 3. For NP, we have 1, 2, so just a distance of 2. And LN is 1, 2, 3, 4, 5. So just a distance of 5 there, okay? When I was doing this in class, some students were saying, negative distance. So, oh, the distance between JK is -3 or something like that, right? I'm here to tell you that distance can never be negative, right? Now think about it intuitively. You're probably sitting at a desk right now, and look at the closest wall to you. Well, let's say the wall is about 5 feet from you, right? There's no way you are you're -5 feet from the wall. Right? There's no such thing as negative distance, negative length. There's just 5 feet in front of you, behind you, to the left, to the right of you, whatever. So the distance is always going to be a positive number. There's always space between 2 things. It can never be negative. Okay, so keep that in mind. Let's go to example 2 here. Determine whether CB, line segment CB, you see the little lines there? It means line segment, right? Line segment CB and line segment DF are congruent. If you remember from last class, if you look at your notes, you could pause the video now and take a look if you want. But the term congruent just means identical or same. Specifically with line segments, it's the same measure. So this question is really asking, do CB and DF have the same distance between them or the same measure? Well, CB has 2 and DF has 1, 2, 3, so the answer, of course, is no, right? 2 does not equal 3, so they are not going to be congruent. Okay, on this slide, go ahead and take about a minute to do the same kind of analysis. Okay, pause the video and then check your work when you're ready. Okay, so let's look at BD and DF. So BD has 1, 2, 3, 4, 5, 6, 7, 8 between it. DF has 1, 2, 3, 4, 5, 6, 7, 8 as well. 8 does equal 8, so they are going to be congruent. Next one, AC is 1, 2, 3, 4, 5, and DE is 1, 2, 3, 4, 5. So 5 does equal 5, so yes, they are congruent. And lastly, CD is 1, 2, 3, 4, 5, 6. And DF is 1, 2, 3, 4, 5, 6, 7, 8. 6 does not equal 8. They are different numbers, so therefore they are not congruent. So that's going to be a big fat no right there. Okay? Okay, so let's move on to the big boy stuff. So let's start with this. So ask yourself, can we find the distance of these lines? Let's start over here on the left. Can we figure out easily what the distance is of this line segment on the graph? And I would say the answer is yes, right? All we have to do is count. So 1, 2, 3, 4, 5, 6. So there's a length here, or a distance of 6 for this line segment. Now let's go over here to the right. Can we figure out what the length or distance is of this line segment? Okay, take a second to think about it. Maybe pause the video. Okay. Well, the answer for this one, to the surprise of some of you, is actually going to be no. You know, what a lot of students do, what I see, is they try to go 1, 2, 3, 4. Oh, it's like 4, 5, 4.5, right? They try to count diagonally there, and that method actually cannot work for lines that are diagonal like this. It can work for ones that are horizontal, like over here on the left, or it could even work for vertical, up and down, right? But when it comes to diagonal, it can't really. Now, oftentimes, you're going to get a decimal number, so like a 7.2 or like a 12.6, you know, something like that. So it's pretty much impossible to count with your fingers and eyes to figure out the distance of this kind of line. And so for lines like this on a graph, we have what is called the distance formula, which we'll use here in example 3. Okay. There are two ways actually to find the distance of something like this over here on the right. We're going to talk about both of those ways, but the primary way that we should be focusing on is what's called the distance formula, which is d equals the square root. Right? Square root is just opposite of square. The square root of x2 minus x1 all squared plus y2 minus y1 all squared. Now take a second to think about what the x's and y's are referring to. What do those mean? Why are they there? All right. If you remember the last slide, we're dealing with graphs, right? And we know graphs, and from our definitions, that we're going to be dealing with coordinates, right? X comma y values. And so these x1s, x2s, y1s, y2s are going to be two separate points. Okay? So let's see. Let's go ahead and use the distance formula. Let's see. We'll copy the problem first over here. Now let's go ahead and copy the distance formula just for easy reference. Okay, so we simply just want to find the distance between J and K, so these 2 points. Now you can imagine these 2 points on a graph if you want, but that is not necessary for this kind of problem. So let's go ahead and just plug everything in. Now what I always recommend to my students, always, to prevent you from doing a bunch of work and then getting it wrong because you accidentally made a mistake by switching two numbers. What I always recommend is labeling all of your numbers. So let's label the first point, point 1 here, J. Let's label that x1 for 4 and y1 for 3, right? And then for -3, we'll call that x2. And then for -7, y2. Okay, remember the x's and the y's are always together. And then the 1s and 2s are always together as well. Okay, we cannot mix and match. Now, if you really wanted, you could put, x2 and y2 over here for J, and x1 and y1 over here for K. That would work, but make sure you don't do anything else. Don't mix and match the 1s and 2s and stuff. All right. So with that, let's go ahead and just plug everything in. So we have d equals the square root of x2. x2 we said was -3. Minus x1 we said was 4, all squared, plus y2 we said is -7, minus y1 we said was 3, all squared, like that. Okay, from here we just simplify the parentheses, PEMDAS, right? So we have the square root of -3 minus a 4 is going to be -7 squared, plus -7 minus another 3 is going to be a -10 squared. Okay. Now what's beautiful about the distance formula is you are never, ever, ever going to get negative numbers, right? Just like we were saying earlier, there's no way there's going to be such thing as a negative distance. And you're never going to get a negative number because you're always going to be squaring your numbers here. So whether you have positive or negative, no matter what, when you multiply them, they will come out as a positive number. So when we have negative 7 squared, negative 7 times negative 7 is a positive 49. Plus negative 10 times negative 10 is a positive 100, like that. Okay. Now from here we just add these together. So we have the square root of 149, 149, something like that. Okay, and then you either have to simplify the radical here, or more accurately, you should get a more concrete number with decimals, right? In the real world, when we're talking to contractors and things like that, they don't want to know that our distance is the square root of 149. They want to know it's something like 18.6 miles or 3.2 miles, right? They want something more exact. So when we have something like the square root of 149, all we're going to do is plug this into a calculator, okay? And you can use anything you want. The Desmos calculator, something like that. Scientific calculator. Okay, Desmos calculator is usually good. So we're going to go ahead and click this square root button, boom, and then 149, and it tells us that the distance in the end is going to be 12.2. 12.2. Okay, so in the end, the square root of 149 is going to equal 12.2 units. Okay, so the distance between those 2 points on the graph is going to be 12.2. And so that's a good highlight of the concern from earlier, right? You can't just count the diagonal lines because oftentimes you'll get a decimal like this, so it won't work. Okay, very good. So let's go back and have you do an example here. Let's see, actually, you know what? Let me actually go over the second method first, and then I'll let you do an example any way you'd like. So as I was saying earlier, there are two ways to solve these problems. The first way is using the distance formula, like we just did. And the second way was using the Pythagorean theorem, like we're about to do right now, okay? If you need a refresher for Pythagorean theorem, there's a video that is linked here on the PowerPoint, on the slides, you can access on Google Classroom. If not, there's a million resources online on how to use it. But all we're going to do here is we're going to find the distance of between these 2 points, just like we did in the last problem, except now the points are on a graph. Okay, so when the points are on a graph, it opens it up to where we can actually now use Pythagorean theorem quite easily to solve for the distance. So I'm going to copy that image. I'm going to go over here. We are going to paste the image. Okay. And then let's go ahead and solve for this. Okay, so this time we're just going to use the Pythagorean theorem, which is a squared plus b squared equals c squared, right? And so all we're going to do here is we know that we want to find the distance or the length between these 2 points. So we're going to draw a line from A up to B like that. So we want to find the length of that line. What we're going to do next is we know we could only use the Pythagorean theorem with right triangles. So we're going to use this line to form a right triangle. Okay, maybe draw a line down here. Okay, draw a line down here. And so with that, we've now formed a right triangle. Now, something that's important to note for this problem, the graph is in twos. okay, which is unusual. It's, not because we're doing Pythagorean theorem or anything. It's just an unusual problem. But just know that every time we count, there's going to be 2's where the numbers are, okay? But it doesn't matter so much. So to use Pythagorean theorem to find the distance here between A and B, we know that we can label the sides accordingly. C, the hypotenuse, will always be opposite from that 90-degree angle. So if the 90-degree angle is here at the bottom right, we know the opposite side is over here. So this side is going to be C, our distance, right? And then we can label the bottom one A and the side length over here B. Doesn't matter A and B, right? You can switch them, doesn't matter so much. C does have to be there though, okay? Now from here, we'll go ahead and do some accurate counting and set up the Pythagorean theorem and plug stuff in. So we're going to start with A. A is going to be from -6 to +5, right? From this point all the way over here is going to be a total of 11. So the bottom here is going to have a length of 11, right? Because remember, we're in 2's, so don't let that fool you. If we start at -6, we end up at +5, so that's 11. So we'll plug that in for A. So we have A squared is 11 squared plus B squared. Down here, we start at -4, and then we end up here at +9. So to go from -4 to +9, that is a distance of, or length of 13. So we have 13 there. So 13 squared equals, and then C squared is what we're trying to find, right? So C squared, okay. Then we just square our numbers here. So we have 11 squared, or 11 times 11 as 121, plus 13 squared. 13 times 13 is 169, which equals C squared, okay. Let's go ahead and add the like terms. So 121 plus 169 is going to be, I believe, 290, which equals C squared. And then the last thing we want to do here to get C by itself is to then square root it, because the opposite of a square is a square root. And so when we do that, the square root and the square cancel out, so we're left with C. But when we square root one side, we have to square root the other, like this, right? And so when we have the square root of 290, let's go back to our calculator here and figure out what that is. We'll go, let's see, clear. We'll do the square roots of 290, and that is going to be 17.03. So we'll write 17.03 here. We'll try to keep it to 2 decimal places. So 17.03. Okay, and that's it. So the distance between A and B is going to be 17.03 units long. Okay, cool. So that's the second method. So first you can use distance formula, and second you can use Pythagorean theorem. It typically does not matter which one you use. It's just whatever you're more comfortable with. I will tell you that you can always use the distance formula no matter what, whether you have a graph or not, whereas the Pythagorean theorem, it's usually going to be easier to use that if you have a graph, so you're a little more limited, but as long as you can use either method to find the distance, it does not matter to me. Do whatever you are going to be comfortable with. Okay. With that, we'll have you do one more example here, and we'll call it a day. Okay, so go ahead and pause the video, try out this problem, and then unpause it to check your work. Okay, so over here we have a typical graph with 2 points, and we want to find the distance between those 2 points. So we'll go back to Jamboard, we'll paste it in here. Okay. Now again, it does not matter which method you use to solve for this. You can use Pythagorean theorem, just like we did on the last problem, or you can use distance formula. I'm going to go ahead and use distance formula because it's a little more important. It's a little more versatile. You can use it for all problems, whereas Pythagorean theorem you're a little limited. So I'm going to go ahead and use distance formula for this one. So we know distance formula, so d equals the square root of x2 minus x1 all squared plus y2 minus y1 all squared. Okay. Now, once again, I highly recommend you label your points so you don't mix things up. So it doesn't matter which one we choose. I'll just start with L, and we'll call that one x1, comma y1. And then for M, we will call that x2, comma y2, like that. And then we will just start plugging everything in. So we have x2 is 4, minus x1 is negative 2, so minus a negative 2, all squared, plus y2 is going to be 0, minus y1, which is a negative 3, so minus a negative 3, all squared. And then let's go ahead and simplify. 4 minus a negative 2, right? Minus a negative, you know, is going to cancel out to just plus. So really we have 4 plus 2, which is 6. So 6 squared. Plus 0 minus a negative 3 is going to be 0 plus 3. So that's going to be 3 squared. Okay. 6 squared is going to be 36. Plus 3 squared is going to be 9. And so we are going to now have the square root of 45. All right. And so really, when we go to the calculator to get the more exact method, we have square roots of 45 is going to be 6.71. So we'll go with 6.71 here when we round it. So that's going to be equals 6.71. Okay. And that is going to be the distance between L and M. If you want to use Pythagorean theorem, you totally could. Just draw the line between the points, the right triangle. Doesn't matter if you draw it down here or up here, you're going to get the same answer and distance regardless. But if you use that method, then that totally works for me. It works for you. Okay. And with that, I have one more slide here just for the honors classes, so don't worry too much about that. And then here's the homework. Homework is just from lesson 1-4, distance, 1, 7, 13, 15, 17, 19, 21, and 25. If you're in honors geometry, go ahead and do 47 as well. Okay. With that, I'll see you for the next lesson. Take care.